In this video, we'll derive the equations of motion for the transverse vibrations of a string under tension. In the figure, I've drawn a set of axes. The x is the axial axis, and the z-axis is the transverse axis. And we have a string of length L, and to the string is applied some sort of distributed load, which I've drawn in green, and we've called f of x and t. Generally, it's a function of x and of time. So the idea here is we'll take a differential slice of the string. I'll just draw it here, and we'll call this ds. It's just some differential length. And I'm going to draw it down here, zoomed up, and I'll exaggerate it somewhat. Obviously, I've exaggerated the displacement of the string in the diagram. We're going to assume that the displacements are small, however. So I've got this differential slice of length ds. Let me draw that at the bottom. And the dotted line here will show the horizontal direction of each face. And then we've got some distributed load up top. I'll draw it in green again, which is f of xt. And then at each end, we have a tension force, tensile force, I should say, and we'll call that P. I'll draw that in red. And down here, it's in the opposite direction, P. And this edge of the string is at x. In fact, I'll draw it up above first. That's x. And the end of the string is located at x plus dx. And then what I'll do is just do it on this diagram below too. So the left edge of the diagram, the left edge of the differential element, I should say, is located at position x, and the right end is x plus dx. The angle is theta over here, and we'll call this angle theta. And I should mention, even though I've called it theta at each end, theta and p at x in general is not the same as theta at p at x plus dx. Okay, we're not going to make that assumption at this stage. I'll also say that the string has some density rho, which in this case is mass per unit length rather than mass per volume as we usually define it. All right, and the idea is I need to apply Newton's law to this differential slice. So let me write that out, Newton's law. Which is just to say F equals ma. So let's look at the ma first of all. The mass per unit length is rho. So the mass of this differential element is rho times dx. Remember that this length here is dx. All right, so rho times dx times the velocity. Now remember, we're looking at displacements in the z direction, transverse displacements. So we'll call that coordinate w. So w, which is a function of x and t, and I want to take the second derivative. So d squared w by dt squared, and w is a function of x and t. And that is equal to the sum of the transverse loads. Well, the first load we have is this distributed load F. The actual load on that element, because F is per unit length, is F of xt times dx, which is the length. So that gives us a force. And then, of course, we need to look at the vertical or the transverse components of P. So I'll draw that in blue. P has a component, we'll say it's up on the right and down on the left. And I'm actually going to write it in here in blue just to keep it clear. So first of all, in the positive z direction, we have that contribution on the right, which would be, I'm going to write it as p sine theta at x plus dx minus p sine theta at x. Why the minus sign? Because these forces act in different directions. On the left side it's negative, and on the right side it's positive, as I've drawn it. All right, so the next thing that I can do is I can divide everything by dx. And on the left side, I'm going to get rho. I'm going to drop the x and t dependency. It should just be assumed, but I'm going to do it for shorthand. W double dot, which is the shorthand of writing the second time derivative of w, is equal to, on the right, f, since I've divided by dx. In fact, let me write that. Divide by dx. All right, and then I'm going to group this term as follows. It's p sine theta at x plus dx minus p sine theta at x, and that whole quantity is divided by dx. Now that should look familiar. As I take the limit as dx goes to 0, which I remind you dx is infinitesimal, then this is just exactly the definition of a derivative. All right, the derivative of p sine theta. It's the difference in p sine theta across a differential element as the length of that differential element goes to 0. So let me rewrite this as rho w double dot is equal to f plus the derivative d by dx. I'm taking a partial derivative because this is all a function of x and t in general, and it's the derivative of p times sine theta. Okay. Now we can further reduce this. I'm going to do this in a different color just so I can keep it separate. Let me do it in purple here on the right. That we've got this differential element of length ds. That's ds. And we can break that down into an x and a z component, so it would look something like this. So this would be dw, and this length would be dx, and this angle would be theta. But for small displacements, which is the assumption here, so for small w's, this is to say if dw is very small, or if theta is very small, it's the same thing we're saying, then ds and dx are approximately equal. So let me write that all mathematically. So what I'm saying is that sine of theta is equal to dw divided by ds, excuse me. Okay? And I'm going to say that tangent of theta is equal to dw, not a differential, take a total derivative at this point, dw by dx. Okay, but if theta is much less than 1, which is to say small displacements, then ds and dx are equal. And we know that from trigonometry that for a small theta, sine theta is approximately equal to theta, which is approximately tangent of theta. So we would say that sine theta is approximately equal to tangent of theta, which is equal to dw dx. So what have I said? I've said that for small displacements, sine theta can be approximated as dw dx. And we're going to plug that result into our derivation. So this can be rewritten as f plus d by dx of p times, and I'll now use partials since w is a function of x and t, dw dx. Okay? Now for constant p, and I explain in a second why constant p is actually a good assumption here. But we can then rewrite this as rho w double dot is equal to f plus p times d squared w dx squared. Okay? And for shorthand, I'm going to actually just rewrite that as w comma xx, just to keep this more compact. W comma xx is the partial derivative of w, or the second derivative of w with respect to x. All right? And then finally we can say, oh, why is it okay to say that p is approximately constant? Because if we look at the horizontal component here of p, we see that that's equal to p cosine of theta, which is approximately equal to p. Why? Because for small angles, cosine theta is equal to 1. Right, I'm going to delete it to make space, but the point is that I'm making is that p is constant. That p at x is the same as p at x plus dx. Why? Because this differential element is not moving in the horizontal direction. So therefore the loads on each side are balanced. Therefore p is constant. So that's why this assumption here of a constant p is perfectly valid. It's valid on the condition that there is no horizontal displacement, and that's based on the assumption of small displacements. All right. And then finally I can say that for free vibrations, this implies that f is equal to 0. And this can be rewritten as rho w double dot, and I'll put back the x and t dependency now, is equal to p times w of xt comma xx. This can be rewritten in a well-known form as w double dot is equal to c squared w comma xx, where c is equal to the square root of p divided by rho. And this is known as the wave equation. And I've shown this in other videos where we come up with a wave equation. Notably in the case of longitudinal vibrations of a bar. If we had a bar like this, and there was a load like that to a horizontal load, or I should say an axial load, then the axial vibrations of a bar yield exactly this wave equation of this form. All right? So we have a second order partial differential equation. It's second order in time and second order in space. In the case of this wave equation, c is p over rho, but in the case of the longitudinal vibrations of a bar, we saw that p was equal to e over rho, or square root of e over rho. So what this is telling us is the tension p kind of acts like a stiffness. All right? What am I trying to say here? Well, the string itself has no stiffness. It's kind of like a wet noodle. What gives the string some stiffness and what allows it to vibrate is the fact that there's tension. All right, so turning the page, and let me just rewrite it here. We have w double dot is equal to c squared times w comma xx, and I'll remind you that c is equal to the square root of p, which is the tensile load in the string, divided by rho. And that is effectively the same equation that we got for longitudinal vibrations of a bar, where we had it in the form of u, the axial displacement, instead of w, the transverse displacement. But it was u equals c squared u comma xx. And in that case, c was equal to square root of e over rho. And I should just mention that these two rows are not the same. In the first case, this row is density or mass per unit length, and this row is the standard definition of density, which is mass per unit volume. But the form of the equations are identical. And let me mention again that this is the wave equation. And we saw that in longitudinal vibrations. Longitudinal vibration of a bar. We saw it in the torsional vibration of a shaft. Exact same equation, the wave equation. And of course, in this case, we saw it with transverse vibrations of a string under tension, I should say. It's transverse vibration of a string. And here is a link to where we solved this equation, these equations of motion, for the case of the longitudinal vibration of a bar. I'm not going to go through step by step, but I will mention what we did. We, of course, used the method of separation of variables. Separation of variables. And what that consisted of was rewriting W. In that case, we did it for U, but same idea. We take W, x of t, and we say that that could be written as a time-dependent part multiplied by a spatial-dependent part. So we'll call it W. This is now capital W of x times capital T of t. So we have a space-dependent part and a time-dependent part. And I can cut to the chase and tell you, again, you can click on this link and go and see how we derived it, or how we solved it, I should say. But the solution is, of the time-dependent part, t, is C1 cosine of omega t plus C2 times sine of omega t. And for the W equation, we ended up with something very similar. C3 times cosine, instead of omega, it's omega over c times x. Omega over c times x, which I write like that, plus C4 times sine of omega over c times x, or omega x over c. All right. These two equations have four unknowns. Because it's second order in time and second order of space, we need two initial conditions and we need two boundary conditions. The two initial conditions are just the typical ones we see over and over again, which is at time equals 0, we know the displacement field, so we know the shape of the string, which is to say W, this is now small w, of x comma 0 is equal to some known w sub 0 of x. So we know what the shape is initially, and also at time equals 0 we know the derivative. In other words, we know the velocity of every point along the string. So the time derivative, which we'll call w dot sub 0 of x. So the two initial conditions are that we know what the shape of the string is and we know the velocity at all points down the string initially. And the two boundary conditions that we typically find, you can have some other exotic ones, but the ones that is most common is that the string is pinned at both ends. I remind you that we can't have a free end in the case of the vibrating string, because if one of the ends was free and there was no traction applied, we would lose all the stiffness. Why? Because this P would go to 0. Okay, in other words, we need tension in the string, so the string must be fixed somehow at both ends. So that is to say that at x equals 0, the displacement is 0. So it's W of 0 comma t equals 0. And similarly, at x equals L, W of L at L comma t is equal to 0. And we'll say that that is pinned at both ends. And we have another example of how we solve for omega. Omega is fundamentally the eigenvalues, and we find it by plugging in the boundary conditions, and we get some sort of an equation that can get solved for W, for omega, I should say. This is omega, this is W. I don't mean to confuse you with those two. Okay? So omega, which is the frequency of vibration, is there are an infinite number of frequencies of vibration because it's an infinite degree of freedom problem. It's a continuous system. And those are known as the eigenvalues, and the shapes, the mode shapes, are known as the eigenfunctions, as opposed to eigenvectors that we see in discrete systems. That's all I'm going to say about this now. I think I might do another video on specifically solving the response of a string that's pinned at both ends, so for these boundary conditions. But for now, we'll leave it here. I hope you found something interesting in this video. If you did, please go ahead and leave us some comments below, or better still, why don't you subscribe to the channel? Thank you very much for watching, and we'll catch up with you in the next video.